northern hemispheric average temperature. And these we call reconstructions because they are derived from tree rings and sediment cores, and they're not temperature thermometer readings, they are estimated. You'll also see the curve from Mann, Bradley and Hughes in here. It's a so-called hockey stick. It's in there. And you can see that these curves are not identical. There are some differences, which highlights the ambiguities in estimating the past temperatures. But nevertheless, you see that they all show similar features too. The temperatures do vary, and there has no time in the last 1,300 years do they suggest that the temperatures are as high as now. And you don't see any similar episode of global warming as you see now. So that suggests that what we are seeing now is forced. So there are several causes that could be possible in principle. And there are three main hypotheses for how solar activity can affect our climate, either through changes in the Earth's in the sunlight intensity or in ultraviolet radiation and how that affects the stratosphere, or through galactic cosmic rays. The most recent focus has been on the cosmic rays, especially in media, championed by the Danish scientist Henrik Svensmark. Let's look at that. Svensmark argues that the cosmic rays are responsible for a significant amount or generation of low clouds. When the cosmic rays reaching us are affected by solar activity, so increased levels of solar activity reduces the amount of cosmic rays reaching us, which again produces fewer low clouds, and hence less sunlight will be reflected, and the Earth's surface will absorb more sunlight. But the cloud generating processes are poorly understood, and there are large gaps of unknowns in our understanding of cloud microphysics. So the primary evidence of his hypothesis is really this correlation. And there are problems with this hypothesis, because if you look at the curves representing the cosmic rays, which is the red one, and the blue curve representing the low clouds, they diverge after 1994. But Svensmark argues that there are errors in the data describing the low clouds after 1994. So he has made some corrections to his data. The scientists who provided the cloud data do not use his corrections. They do not agree. And these corrections are controversial. But we can shed some more further light onto his hypothesis by looking at this graph here. This figure shows a number of indicators of the level of solar activity over the last 50 years. And this is the period when most of the recent global warming has taken place. The blue curve representing the cosmic rays shows no trend. Neither do the other solar proxies. They show no trend, no systematic change, apart from the 11-year cycle. So it's very difficult to use these indicators to describe global warming. We don't see corresponding changes, long-term changes in the sun. This figure shows the temperature changes over the last 50 years. This is from the ENSAT reanalysis, by the way. Some skeptics argue that the part of the trend is due to changes in the land surfaces or due to urbanization. But changes in the land surfaces or urbanization do not readily explain the changes in the sea surface temperatures, in ocean heats, in the sea level height rises, or in the glaciers, or in the Arctic sea ice, or not even in the warming over the Arctic, because there are not many cities there. Okay? So that leaves us with greenhouse gases. We know that CO2 is a greenhouse gas. In fact, but this curve shows how the greenhouse gas has changed over time, and this curve is known as the Keeling curve. In fact, the CO2 is not counted one atom, molecule by one molecule. It's basically the concentrations are estimated from air samples from which you measure their ability to absorb heat rays. So in fact, the Keeling curve tells us something about how, the atmosphere's ability to absorb or trap heat rays. But how do we know that the CO2 that we see here come from fossil fuels? The carbon atom can have several numbers of neutrons. The different types of atoms have different atomic weights, 12, 13, or 14, which are called isotopes. And the isotopes in CO2 measurements, like the Keeling curve, leave fingerprints which point to fossil fuels. Also, if you look at the amount of CO2 there is in the atmosphere, that more or less fits in with the amount of emissions which has been calculated from fossil fuels. We also see a hemispheric gradient in the CO2 flux, suggesting that the sources are in the northern hemisphere where the fossil fuels are burned. We also see that the ratio oxygen to nitrogen is declining, which fits well in with the chemical reactions or equations which describe the burning of fossil fuels. The oceans are becoming more acidic due to increased uptake of CO2. So there are many indicators suggesting that this is from fossil fuels. And basically, there's more carbon now on the Earth's surface because the use of fossil fuel means taking carbon from the depth of the Earth and injecting it into the ocean and the atmosphere. First the atmosphere and then the ocean. Gavin Smith and I studied the climatic response to solar forcing and greenhouse gases. We analyzed a set of climate model runs with and without solar forcing and with and without greenhouse gases. And these are just some of our results. And the red curve shows the observations and the blue curve shows the model data. And you see there's a fairly good fit between these. The symbols there show predictions made through an analysis where we used solar forcing and greenhouse gases to predict the temperatures, or these curves here. Basically, the main conclusion from our study was that the analysis, which can tell us something about the importance of the different factors, the solar forcing cannot explain more than a small fraction of the warming. You really need greenhouse gases in order to describe most of this. The climate models indicate that the air temperature